Good day, I'm Jagdish Singh Samant. I'm here to talk about POP-VQA, which stands for Privacy Preserving On-Device Personalized Visual Question Answering, on behalf of my team from Samsung Research Institute, Bangalore. In this era of large language models and robotics, a personalized assistant is not in the future, it is happening now. The backbone of this kind of assistant is to have the visual question answering ability. And the real benefit of such systems is when they are personalized and should be able to work without internet and also preserve users' personal data. Solidify my point on personalization, I want to take you through this example where for a given image and a question, the general system returns boy is playing with blocks while the personalized system returns Tom is playing with blocks, which is more informative. We propose a system that can effectively use on-device personal knowledge to enhance system's answer. We build a pipeline that can use any sort of VLM model to build a system that can provide offline personalized interaction. We compared our solution to the SOTA available and it is 36% more accurate. We also conducted a user extensive study, and through this study, we got to know that 95% of them wanted to have a personalized solution on their devices. Now, I want to take you through architecture and pipeline. First of all, we'll discuss the model expectation. We want to have a model that can give general questions answer and also take benefit of on-device personal knowledge to give a personalized touch to pers- those answers. And also we want to have the ability to identify people in the image to form the relation between them, and while doing this we want to preserve users personal data. These are the data set we are using, and this is the pre-processing state. Now I want to come to the challenges. The first challenge is to find a data that has personal knowledge information embedded, and a way to incorporate on-device personal knowledge to our system and a technique to identify people. I want to take you through this example to prove why we need to identify people in the image. For this question, who is standing on right of Narendra Modi, we won't be able to give the answer if we don't know who is Narendra Modi. And finally, we want our model to be of a small size with less training cost. This is our complete architecture. I will take you through this architecture in the later slides. During data curation, we came across two kinds of VQA datasets. The first one is general VQA, which has huge number of general VQA, general question answers. And the other one is knowledge-based VQA, which has question answers and personal knowledge information. We want to have the best of the both world to fine-tune our model. We combined those two datasets in 60-40 ratio and took 12 types of entity relations from KVQA based on our product's target. During training, we are getting knowledge information from KVQA dataset, and during fine-tuning, we are using personalized personal knowledge graph to get that information. A personal knowledge graph is a graph where user is the central node and all the edges are entity relations and the rest of the nodes are rest of the entities. Personal knowledge graph gets its information from user calendar, photo metadata, gallery database, etc. For a chosen image, we get personalized information from personal knowledge graph and fed it into the pipeline to get the answer. We are doing pre-processing because we want our model to pick the correct answer, not to learn the correct answer. To explain this point, I want to take you through this example. For this question, we want our model to get the right bounding boxes to Narendra Modi and then map it to Xi Jinping, not to learn directly Xi Jinping as the answer. We are doing these three things during pre-processing. During training, we are using MTCNN to get the bounding boxes, and during inference, we are using facial recognition system to get the bounding boxes. At training time, we are using KVQA dataset to get the entity relations, and during inference, we are using personalized knowledge graph to get those entity relations. And then we are combining it with the question and feeding it to our training pipeline to get the answer. Now I want to discuss about our models architecture. We are using OFA-based pre-trained model. We are using pre-trained model because we don't have the resources to train it from scratch. OFA-based is a transformer-based architecture which uses VIT as their vision encoder and BERT as their test encoder. Why OFA? Because one, it is of a smaller size, and second, it uses visual grounding during pre-training. And we hypothesize that visual grounding is going to help correlating bounding boxes with faces. To prove our hypothesis, we trained two VQA SOTA models, LXMUT and LBEF, and compared it with our upward fine-tuned POP-VQA model. The results of which are present in this chart. In this chart, I want you to focus on the spatial category, and we saw a huge accuracy bump on this category of question, and this proves that visual grounding is helping here. Now, I want to talk about post-processing. We are post-processing our general answer to have the personalized answer using the personal knowledge graph information. Now I want to take you through our model's performance with comparison to SOTA available like MemNet and Unitar. In almost all cases, our VQA is outperforming those SOTA models. Now I want to take you through these three main points. We saw 36% accuracy bump on one-hop data, and we attribute this improvement to the improved training of self-attention layers. We saw 74% improvement on accuracy improvement on spatial data, and we incorporate this to the visual grounded captioning used during OFA pre-training. And in subtraction data, we didn't see any significant improvement. And on investigation, we find out that our model's answer is very close to the actual answer, but not exactly same. And we also want to determine why is this happening and how we can improve that. After fine-tuning on KVQA dataset, POP-VQA's performance on VQA 2.0 data is get reduced. To enhance the performance on general VQA, we trained it on the mixture of KVQA and VQA 2.0 dataset, and the results after training are shown in this chart. And from this chart, we can say that after fine-tuning, it is at par with OFA base while retaining better accuracy on KVQA dataset. To check the robustness and real-world applicability of our solution, we test our solution on users' personal data. For that, we get 1500 images and 5000 questions from user and plot that against OFA-based model. The results are in this chart. From this chart, it is better than OFA-based. We couldn't compare it with SOTA models because of the data format mismatch. To understand the true impact of our proposed solution, we conducted a user study consisting of 100 users. We integrated our solution on their personal devices and allow them to ask the question on their images. The results of this study are shown in this table. And from this table, it is clearly that on every matrix, the POP-VQA is performing better than the generic VQA. And almost all users agreed that they want personalized solutions on their devices. These are some user example from our demo devices, and you can find more of this kind of example on our paper. To summarize, we build a personalized on-device that can work without internet for personal interaction solution, which is 36% more accurate than the currently available SOTAs, and it takes only 0.7 seconds on Samsung S23 Ultra. The scope of improvement is there. We are using only one hop types of questions, and for improvement, it can be extended to multi-hop questions. For future work, we are thinking about to get the better real-life experience by training it against gender and race biases, and also wanted to integrate with language modeling systems to have a more interactive dialogue system. Thank you.